Hey guys, how's it going? Alright, so first of all, sorry for not getting this up on the website until Sunday because the school is closed on Saturday and our network was also down, so there was nothing I could do about it. So here I am Sunday, and this is chapter 10. Make sure you have your guided notes. Open your textbook to page 392 because that's where chapter 10 starts. And the good news about chapter 10 is that most of it is going to be a review for you, which is great, but there's a couple new little things that we're going to be adding to your base knowledge. All right, so here we go. Chapter 10, have your guided notes, maybe a calculator out. Here we go. All right. First of all, some characteristics of gases. This is chapter 10, section 1. A lot of the things that they talk about here is that air is a mixture. There was a multiple choice question a while back about what is the basic breakdown of air. You need to know that air is a mixture, mostly made out of nitrogen, about 78%. You can round that to 80 if you want. And the oxygen is about 21%. You can round that to 20. So what's 80 plus 20? Pretty much 100%. So the next most populous gas in the air is argon. So that was a popular question that I saw a few years back. All right, and then the next concept in this section is that gases are squishy. You need to understand that there is a huge amount of space in between the gas particles in a gas. And so we say that they're squishy, they're compressible. In other words, they can exert pressure. And then finally, noble gases are monatomic, and everybody should already know that. And then if you look down at the bottom of page 394, table 10.1 says some common compounds that are gases at room temperature. This would be a great table to refer to every once in a while because this is one of those popular, it has some organic chemistry in here too, which is really important for you guys. But just a reminder on this particular table is there's a particular gas in here that I think is extremely important for you guys to remember, which we can oftentimes forget. That would be SO2. SO2. Do you remember me talking about the compound H2SO3? How this particular gas, if it's being formed, it can oftentimes decompose into H2O and SO2 gas. That's a popular misconception on some of my students in AP chemistry. Another of the popular ones would be, do you remember what the other one was that decomposes into CO2 and H2O? Do you remember what that was? If you ever form H2CO3 as a product, you need to remember that naturally decomposes into CO2 and H2O. And then here in organic chemistry, we've got methane, ethane, and propane. So here's how I remember those. I oftentimes like to tell my students that the first 3 carbons in organic chemistry is a gas. So if you look at this table, you'll see that they start you off with CH4. So here's your first carbon. There's 1 carbon in there. And then the next one is C2H4, which is ethane. So you see how now there's 2 carbons in there. And then the last one is C3H8. And if you look at there's 3 carbons here. So the first 3 carbons in organic chemistry, that's what I usually say, are gases. All right, so one interesting note here is this NO2, nitrogen dioxide. You guys are going to be doing a lab, I don't remember when, but I know you're doing a lab where this particular gas will be released. And please notice in table 10.1 that it says that it is toxic. It is a reddish brown color, and irritating odor is probably an understatement. The odor of this particular gas is so nauseous that it burns the insides of your nose cavities, and it's unlike any other smell you've ever smelled before. If you've never been in a chemistry lab where NO2 was released, let's put it this way, it's something that you won't ever forget, and it's not anything that I can really compare it to. So anyway, all right, so that is 10.1. Okay, the next thing that I want to remind you of is the kinetic molecular theory, or the kinetic particle molecular theory of gases. So gas particles are really small, and they're considered to be moving in very fast, random, straight paths. And they bounce off of each other and the sides of the container that they're in. And when they do that, that's called pressure. Like, that's the whole idea behind pressure, is how often they bounce off of the container that they're put in. And then it says, no energy is lost or gained when particles collide with the container or with each other. So there's no gain or loss of energy in any collisions, which we'll have to talk about later, because as I'm sure you understand, eventually that energy will go down. And anyway, we'll talk about that later. Okay, energy. Two different types. Kinetic energy. Do you still remember the formula for kinetic energy? Potential energy. This is energy that is based upon your position. It is called stored energy, or the potential to do work. It says when gases are heated, the particles move faster and they have more kinetic energy. So one of the things that I need to make sure that you guys realize is that temperature really is a measure of the amount of kinetic energy that the particles have. When the particles start colliding with one another more often, then that can change the temperature. So we'll get to that again later. All right, here are the basic variables that I'm sure you recognize from basic honors chemistry. Capital P stands for pressure, and pressure can be measured in various units here. We've got kilopascals, symbolized as lowercase k. That should be a capital P, my apologies. Lowercase k, capital P, lowercase a, kilopascals. Or atmospheres, or millimeters of mercury, which is also known as torr. Capital V stands for volume in liters. Capital T is temperature in Kelvin, which is really important that we remember that this particular T is very specific. It needs to be in Kelvin. And the lowercase n stands for the number of moles, or number of particles. Okay. Here's a picture on the bottom of page 395. I'm going to start going into 10.2 now. So in this particular section, they're talking about pressure. The whole section is about pressure. And one of the things that I always told my students is that the amount of air over your head is a measure of how much pressure you've got standing above your head, because you need to remember that atmosphere and gas has mass, and it also has weight. Weight is a measure of the gravitational pull on an object. So pressure and weight are somewhat intertwined in this particular section. So this is something that I think you guys may want to write down, because this particular unit is used an awful lot. So 1 meter squared, so that's area, of a column of air for at sea level. So you have to be standing at sea level. At sea level. Has a mass of 10 to the 4th kilograms. You see that? 10 to the 4th kilograms. I'm going to show you how they figured that out. All right, 1 atmosphere of pressure. So in other words, it's got to be at sea level. That is what 1 atmosphere of pressure is equal to. So I'm going to show you the math behind how they figured out this mass, 10 to the 4th kilograms. Check this out. So Earth's atmosphere exerts pressure at the surface of the planet. The mass of a column of atmosphere, exactly 1 meter squared cross-section area, and extending to the upper atmosphere, because once we get into the outer atmosphere, you're starting to talk about stuff that's not really clinging to Earth anymore. So let me show you the math behind this. This is kind of neat. Pressure, if you're a physics person, you may remember this. Pressure is considered to have the units force divided by area. So the amount of force applied over a specific area. Hold on, I'm trying to find a different color here. Here we go. So pressure is equal to a certain amount of force over a certain area. And then you guys should know this particular formula. Force is equal to mass times its acceleration. So I could technically measure the force of gravity on each and every single one of you guys here at Earth. All I need to know is your mass. And the mass needs to be measured in kilograms. And the acceleration, A, needs to be measured in meters per second squared. So again, force is equal to mass times acceleration. Mass in kilograms acceleration in meters per second squared. Well, for us, does this number look familiar to any of you? 9.8 meters per second squared. Guys, that is the acceleration of gravity. Gravity here at Earth can be measured in an acceleration. The amount of acceleration that you have pulling you towards the center of the Earth can be measured in meters per second squared. So if I pick you up and take you up into the sky and I drop you, you will accelerate towards Earth once you overcome air friction and everything. Your maximum velocity or acceleration would be considered to be 9.8 meters per second squared. And then, check this out. This 10,000 kilograms, do you guys remember that from the previous slide? That is 10 to the 4th kilograms. That's the amount of mass that 1 meter squared section of sky above your head. That's how much it weighs. And then we have the acceleration of gravity. So check this out. Your force for a 1 meter by 1 meter square of sky above your head, the force applied in that particular area would be 1 times 10 to the 5th kilogram meters per second squared. So why is this number even important to us? I'll show you. Again, 1 times 10 to the 5th kilogram meters per second squared. Does anybody know what the unit kilograms meters per second squared actually is? Do you know what that is? You should know what that is. That's called a Newton. That is the unit for a Newton. So check this out. What we've got here is the pressure of the atmosphere on the surface of Mercury. So right here you've got a little pool of mercury. And it says represented by the blue arrow. And then, so this atmospheric pressure pushing down on this mercury right here, it equals the pressure of the column of mercury in the red arrow. So here's your mercury inside of this tube right here. And notice that it's closed on the top. That means that there's a vacuum established inside of this tube. And that's a column of mercury. So right now they're at equilibrium. They're in balance with one another. Does anybody know what this device is actually called? It's a very simple tool that we use to measure pressure. We call it, very simple, a barometer. This is the basics behind a barometer. When you guys come in next class, ask me to pull out my homemade barometer, because I made one. Not out of mercury, obviously, but I made it out of water, and it works pretty darn good. I'll have to show that to you guys next class. All right, so back to that last question about the gravitational force or pull acting on the gas above a 1 meter squared section. The SI unit for force is kilograms times meters per second squared. This is also known as a Newton, symbolized as a capital N. It says the pressure exerted by the column is the force divided by the cross-sectional of the area over which the force is applied. So just remember, force is equal to the amount of force over a certain amount of area. And then it says SI unit for pressure is in newtons per meter squared. That is the SI unit for pressure. But guys, you need to know this. There is only one SI unit for pressure. Hold on. Sorry. So there's this, but you've probably never seen that before. You've probably seen this other one, pascals. So some people recognize pascals as being this, kilopascals. Did you realize that a kilopascal is equal to 1,000 pascals, and that a pascal is equal to Newton per meter squared? So this would be 1,000 Newton per meter squared. This right here is how we get to that particular formula. It says a related unit is sometimes used to report pressure, called a bar. You also need to know that 1 bar is equal to 10 to the 5th pascals, PA. All right, so these are some basic units that I think we should all make sure that we try to write down. And in your guided notes, I make you write it down, and that you're familiar with, okay? Because sometimes they'll give you bars, sometimes they'll give you pascals, sometimes they'll give you kilopascals. Just understand that they're all technically SI units, okay? Okay, standard atmospheric pressure. the typical, sorry, typo, the typical pressure at sea level. So here's some major conversions here. We're talking about all the different types of units that we could possibly use. So the number 760 millimeters of mercury is equal to 1.01325 times 10 to the 5th pascals, which is the SI unit for pressure, which is technically equal to 101.325 kilopascals, which is equal to 1 atmosphere, which we're familiar with, which is equal to 760 torr. So remember, millimeters of mercury is the same as torr. And so I just wanted to make sure you see that at the end. So here's all the unit conversions written out for you, and it's all the same to me. You guys just need to get really good at unit conversions with pressure, okay? All right, here's a new device that you've probably never seen before. It's called a manometer. This device is sometimes employed in the laboratory to measure gas pressure near atmospheric pressure. And if you have ever seen one of these, it kind of looks like a barometer, like one of those old-fashioned barometers that you may see like in a fancy-smancy doctor's office. This would be the type of barometer that maybe they might use. So one really important thing to notice here is that the pressure, there's usually a gas inside of this container, which is exerting a pressure on this column of mercury. They usually use mercury right here. And there's an open end, which is open to the atmosphere right here. And this is where I need you guys to look in your textbook at the bottom of page 397 for example 10.2. And here's the question that they put on there. It says, on a certain day, the barometer in a lab indicates that the atmospheric pressure is 764.7 torr. A sample of gas is placed in a flask attached to an open-end manometer. The level of mercury in the open-end arm of the manometer has a height of 136.4 millimeters, and the mercury in the arm that is in contact with the gas has a height of 103.8 millimeters. What is the pressure of the gas in atmospheres and kilopascals? Here we go. So obviously you can look in your textbook, but I want you to really picture what this would look like, because here's your manometer. And I know this is a really terrible drawing, so sorry. And this manometer has an open end that is open to the atmosphere. And the atmospheric pressure on that day was 764.7 torr, which is the same as millimeters of mercury. Don't forget that. Now there's a gas inside of this manometer, and the gas is exerting a certain amount of pressure, and this thing is filled with mercury. So the question is, which side has a higher amount of mercury? Is it the side that is closest to the gas, or is it the side that is closest to the atmosphere? So you really need to think about this gas pushing here and the atmosphere pushing here, and which side was higher. So be careful. It says, we know that this pressure must be, back up. We're given the atmospheric pressure and the heights of the two mercury in the two arms for the manometer, and asked to determine the gas pressure in the flask. We know that this pressure must be greater than the atmospheric pressure because the manometer level in the flask side, 103.8, is lower than that on the side that is open to the atmosphere. So in other words, the mercury is higher on the atmosphere side. So whatever this gas is doing, it must be pushing harder than the atmosphere is, because look, it's higher on the open side than it is on the other side. So here is your H. And this gas must be exerting a larger pressure than the atmosphere because the mercury is pushed over towards the atmosphere. All right, so all we need to do is just figure out the height difference, which is pretty simple. Flip it over to page 398. So the pressure of your gas is going to be equal to the pressure of the atmosphere, the pressure in atmosphere of the atmosphere, plus whatever the height difference is. So the pressure in the atmosphere was 764.7 torr, which is millimeters of mercury, plus whatever the difference was in your height difference. So all we have to do is go like this: 136.4 minus 103.8. And so, pretty easy calculation here. 797.3 torr. All right, now that right there, you need to stop a minute because you have to look back at the original question. Yes, we have our pressure in torr, but they want us to convert that pressure in torr to atmospheres and kilopascals, because kilopascals is our SI unit here. So let's go to 797.3 torr. Do you remember what torr actually technically means? That is millimeters of mercury. So we know that there are 760 torr, or millimeters of mercury, in 1 atmosphere. So this will convert our torrs to atmospheres. That is 1.049 ATM. And then the second step that we need to do is to change that to kilopascals. So I'm going to go ahead and use the answer from the previous problem. ATM. And I know that 1 atmosphere is equal to 101.3 kilopascals. And so that equals 106.3 kilopascals. There's all of our answers. Okay. So my one tiny little hesitation on this particular thing is that I want you to realize that it says, get the differences in height. Please note that the pressure of the gas is greater than that of the atmosphere because the height of the mercury is higher on the arm exposed to the atmosphere. And then, guys, you need to understand that this little plus sign could technically be a minus sign, because if the pressure in the arm, previous. Oh, come on. Previous. Okay. Because technically, if the height in the arm was opposite than what you saw, let me show you. So what if we had the gas contained here? And I know my drawing is really sucky today. And here's the atmosphere pressing down right here. What if the height difference was like this? What if the height was like this? That means that the atmosphere is pressing harder than the gas is, because if you can look, it's higher on the side with the gas. So technically, remember to always watch out for where it says the height arm is, which height arm they're talking about, so that you know that this technically could turn out to be a minus sign and not a plus sign. Okay, next. This is a review from Honors Chemistry, so I'm going to go kind of fast in this particular section. It says, what happens when you add or take away gas particles? So what I'm talking about is changing the variable N. Okay, N represented moles, but N can also represent the number of particles, right? Particles or moles. So it says more particles equals more collisions with the gas particles and the container, which in the end results in more pressure. So that's a review. Changing the volume of the container. You can raise the pressure exerted by a contained gas by reducing its volume. So if I push down on this piston, assuming that there's no leaks or anything on this container, if you press down, it'll give the gas particles less room to roam about, which will inevitably increase their pressure. Increasing or decreasing the temperature. This is a no-brainer. If you have some particles of gas and you heat them up, you will make those particles of gas move faster. And if they're moving faster, they collide with the container more often, which inevitably will increase their pressure. Which brings us to all of the gas laws. This should be a total review for you guys, so let's see how well you do. Boyle's Law. When pressure goes down on a container with gas in it, the volume of gas increases. When the pressure goes up, the volume goes down. So this is an inverse relationship. When one goes up, the other goes down. That's called inverse relationship. And so here is your gas law. P1 V1 is equal to P2 V2. So check out these three diagrams. In the first diagram on the left, the pressure is 100 kilopascals and the volume is 1. But if I release and pull up on this piston to give it more volume, the pressure will go down, but the volume will go up. What is 50 times 2? It's 100. Then check this out. If I push way down on this piston and really give a squeeze to these particles, yeah, the volume goes down, but that means that the pressure would go up. So what is 200 times 0.5? It's 100. Each of these, when you multiply pressure times volume, you will get the same number each time. Here's an example. A hot air balloon contains 45.6 liters of helium at 125 kilopascals. What is the volume when the balloon rises in the atmosphere to a pressure of only 15 kilopascals? So here's the formula, P1 V1 equals P2 V2. And this is your unknown, because when it goes up in the atmosphere, we know its pressure, but we don't know the new volume. It says if you are rearranging the formula for V2, so think of algebra, get rid of P2. It's attached to V2 through multiplication. So if you were to get rid of it, you'd have to divide by P2, and you'll get this ending formula. So all you guys need to do is to plug in the units, make sure that the volume is in liters, which it already is. Make sure that your pressures are the same. You don't want to use two different units. You'd have to do some kind of conversion there. I'm going to put that on your study guide, so make sure you refer to that. Go ahead and pause it right now so that you can answer that question. The next one is Charles's law. This is the temperature-volume relationship. It says under constant pressure, make sure that you are keeping pressure the same, because otherwise you throw in another variable. So it says under constant pressure, when temperature goes up, volume goes up. When temperature goes down, volume goes down too. So think about a balloon, throwing it into the freezer. You're really cooling it down, but you're going to keep the pressure constant because it's in an elastic container. So when temperature goes up, volume would go up, it would expand the balloon, but when temperature goes down and you freeze it, then the volume of the balloon should go down. So this is a direct relationship. So anytime you see a steady increase, when X increases, Y increases, that's called a direct relationship. So looking at this particular graph, do you remember the significance of this particular experiment? This particular experiment, if you check it out, he noticed that there was definitely a direct relationship, and he was using temperature scales in degrees Celsius. And he ended up figuring out that if you connect this line all the way down, you get to a very significant point at which there's no volume. Think about this. In order for something to be classified as matter, it has to have mass and take up space. What happens if you take away the space? All right, so this point right here on the graph became very significant, and I think you guys know what I'm talking about, right? It says, Charles observed that at constant pressure, the graph of gas volume versus temperature yields a straight line. You'll also notice that at a certain point, the gas gets to a certain temperature where the gas has zero volume. William Thomson, otherwise known as Lord Kelvin, predicted this point on the graph because no one could get a material that cold in his time. But he did predict that point on the graph, and that point is known as absolute zero. The temperature at which the gas has zero volume is at negative 273.15 degrees Celsius. This is the temperature at which the kinetic energy of all the particles would be zero. Think about kinetic energy, energy in motion. There's no more motion. And then, of course, I said, is that possible? Can a particle have zero energy? Can a gas have zero volume? It says the volume of a fixed mass of gas, this is Charles's law, is directly proportional to its Kelvin temperature if the pressure is kept constant. So now we've got to keep the pressure constant. It says since there is a direct relationship, then you can write Charles's law as the following. Ready? V1 over T1 equals V2 over T2. That's Charles's law. Here's an example. If a sample of gas occupied at 6.80 liters at 320 degrees Celsius, what will be its volume at 25 degrees Celsius if the pressure does not change? Now, if you remember previously, I showed you a slide. What is the unit that you should be using for temperature? It should be in Kelvin. So how do you change these temperatures to Kelvin? Do you remember what absolute zero was? Negative 273.15. So how do we get these to change into Kelvin? You guys should totally remember that. The last gas law is Gay-Lussac's law, the temperature-pressure relationship. So if you see P over T, just like in Charles's law, okay, you see one unit on top and then you see a divide and a unit on the bottom. My question is this: is that a direct or indirect relationship? You're dividing. Look back at the previous gas law that you just looked at. You should be able to answer that question. Finally, we get to the combined gas law. So totally stressing over how to memorize all of these gas laws. Guys, the combined gas law is each of those gas laws combined. So in the original Boyle's law, you had P1 V1 equals P2 V2. And then in Charles's law, you had, what was that one, Charles's law? I think that was that volume and temperature? I think it was volume and temperature. So V1 over T1 is equal to V2 over T2. And then finally with the last guy, it was P1 over T1 equals P2 over T2. It's all written here. So my question is, what if I hold temperature constant? T1 would equal T2, and so they would cancel each other out. So guys, literally, if you look at this formula and you cross out T1 and T2, whose gas law do you have left? That looks like Boyle's law, P1 V1 equals P2 V2. Next question. Over here says, what if I hold pressure constant, where P1 is equal to P2? So let's now look and analyze if pressure is equal to one another. Get rid of pressure on both sides. Whose law is V1 over T1 is equal to V2 over T2? So you see how you can rearrange this particular formula. It's really easy. Moving on. So far we've talked about temperature, volume, and pressure. The amount of gas in a system, expressed in terms of the number of moles, is symbolized with that N. So when you throw the variable N into the formula, number of moles should go on the bottom, because I don't know if you remembered in my previous slide, if you add more particles to a container, what happens to its pressure? Goes up. So an increase in N equals an increase in P. That's a direct relationship. So it says the number of moles of gas is directly proportional to the number of particles. Moles must be directly proportional to volume as well. Think about that. If you increase the number of particles in there and hold pressure and temperature constant, then volume should increase. It says you then must introduce N in the combined gas law. So this is the real combined gas law with the number of moles on the bottom. The ideal gas law constant. According to the previous formula, PV over Tn, that variable right there, P over V, or PV over Tn, is a constant. So hold on, let me talk about this real quick, because this can get confusing. I'm going to show you on another slide. So here you have this, PV over NT is equal to PV over NT. And these are all the initials, and these are all the finals. If you take 1/2 of this expression and you plug in some of the constants, like, guys, what is the standard temperature for a gas? What's standard temperature? 0 degrees Celsius is standard temperature, but in Kelvin, that's 273.15 Kelvin. Now at standard temperature, so at STP, standard temperature pressure, STP, do you remember this? What is 1 mole of gas at STP? 1 mole of any gas at STP is equal to 22.4 liters. So what is standard temperature and pressure? Standard temperature is right here, but what's standard pressure? Standard pressure is equal to 1 atmosphere. which is equal to 760 torr, which is equal to 101.3 whatever kilopascals. So check this out, guys. Here is the temperature that you're going to plug in for a standard gas. Here is the volume that you're going to plug in for a standard gas. Here's the number of moles that you will plug in for a standard gas. And, oh no, we have 3 different types of pressure that we can plug in for a standard gas. When you plug in each of these variables, so for pressure there's 3 different ones, but when you plug in 22.4 here, 273.15 here, 1 here, you come up with a constant. And I challenge you to figure out where this constant comes from. The constant is called the gas law constant, the ideal gas law constant, and we symbolize it with a capital R. So what you inevitably get is this. R is equal to P2 V2 over T2 N2. Now, if you rearrange this formula to get rid of the T and the N on the denominators, check this out. Multiply it by T, multiply it by N, and whatever you do to one side, you got to do it to the other side, T and N. You get this. T N R is equal to P V. Guess what the ideal gas law constant, or the ideal gas law equation formula is? PV equals nRT. That's how we traditionally express the ideal gas law. So what is the value of this R? Do you remember all the values of R? Let's show you. Oops, what happened? Hello? Where's my computer? It's my computer chugging. Whoa. Hey, there it is. Hold on. Slideshow. Whew. There it is. Okay. It says you can find R given the important fact about gases. 1 mole of every gas occupies 22.4 liters at STP, which I gave you 101.3 kilopascals and 273 Kelvin. So check this out. This is what R is equal to, PV over Tn. If you start plugging in all of these different variables for pressure, remember there's 3 different ones for pressure, but all of these 3, the volume, the temperature, and the number of moles remains constant. If you do that, check out your 3 different values of R. R can equal, depending on the pressure, so this is like super important that you remember it depends on the pressure. R can be 8.31 if you're talking about kilopascals. It can be 0.0821 if you're talking about atmospheres, or it can equal 62.3 if you're talking about millimeters of mercury. So there are your 3 variables of R, the ideal gas law constant, and it depends on P, what value of P you're using. And I already showed you this. PV is equal to nRT. That's the ideal gas law. Here's an example. You fill a steel container that has a volume of 20 liters with nitrogen gas to a final pressure of 2 times 10 to the 4th kilopascals at 28 degrees Celsius. How many moles of N, nitrogen, does the container contain? It says, remember, you must convert degrees Celsius to Kelvin. All right, here we go. Let me choose a different color besides red. That doesn't show up very good. Okay. So you have a volume of 20 liters. It doesn't look like that changes because it's in a steel container. So there's only 1 volume. You have a final pressure. Here's your pressure right here. And you have a temperature right here. And it says how many moles of N does the container have? So this should be like a dead giveaway that if you only have 1 volume, 1 pressure, 1 temperature, and they're asking you for moles, this should be a dead giveaway to use PV is equal to nRT. So the first thing we're going to do is convert that temperature out of degrees Celsius. So 28 plus 273.15. And I know some of you guys are going to be like kind of worried about your sig figs here. but I'm not going to worry about that right now. It is 301.15 Kelvin. So there's our T. Let's see, your V is 20.0 liters. Let's see, so that's T, that's V. We've got pressure in kilopascals. So we have to be careful then about which value of R we choose to use. So since your pressure is in kilopascals, I want you to go back and look, what is the number of R when you have kilopascals? So look over here. Your value of R when you have kilopascals is 8.31. So we should be using this R, 8.31. All right, so pressure, we're putting in the number 2.00 times 10 to the fourth kilopascals. V is 20.0 liters. We don't know N, that's what we're trying to solve for. But R is 8.31, and if you really want to go crazy with your units, be my guest, but it's 8.31. And your temperature should be 301.15 Kelvin. So use your algebra skills to solve for your unknown right there. Let me, real quickly on my calculator, check for the correct answer. And then you guys just have to kind of figure it out on your own. Okay, I get a final answer N equal to, and I'm going to go ahead and shoot for 3 sig figs because I'm looking at this 2.00 and I see this 20.0. So I'm going to shoot for 3 sig figs on this and call it 160 moles. Now you guys check your math and see if you can get that as your final answer. Okay. So this is just showing you how you can rearrange the formula to solve just for N. You should have put 8.31 and the temperature 301 Kelvin down here on the bottom. And I don't want to show you the answer to that, so okay, the next section is 10.5. It says further applications of the ideal gas law. Alright, so check out 10.5. It starts here on page 406 of your textbook. I want you to notice something really cool. It says densities and molar masses. So it says, what if we multiply both sides of this equation by its molar mass? So it says see page 406 to 407. I'm going to show you here on another slide here. This is critical. Check this out. This is the ideal gas law, just kind of rearranged a little bit. Okay, that technically is the ideal gas law, just kind of rearranged mathematically. So what if we multiply both sides of the equation by something called molar mass, which is symbolized with this really pretty cursive M. So molar mass. What are the units for molar mass? Sometimes people get really confused by this. Molar mass is technically equal to the number of moles. Oops. Oh, I'm sorry. Erase that. That's not true. Molar mass is technically equal to the number of grams per mole. So that's a unit for molar mass. So now I'm going to start showing you some units on all of this stuff, including this R thing. All right, so we need to talk a little bit about what happens to molarity when you do that. All right, so here we go. We are going to multiply both sides by molarity, and instead of using in the book, it uses that fancy smancy looking M thing. I'm going to do this. Oops, God, I keep doing that. I'm going to do this: grams per mole over here, and grams per mole over here. So now I'm going to show you what this becomes down here. N is moles. V is liters, right? Pressure can be in like atmospheres, kilopascals, whatever. I'm going to do the kilopascals. R. You ready for this? R can be kind of tricky. So since I'm using kilopascals up here, I'm going to show you what R becomes down here. So if you don't remember, look back on the PowerPoint. Hold on, let me go back. Okay, check out R. It is liters times kilopascals per Kelvin mole. Liters times kilopascals per Kelvin mole. Hold on, where'd my previous slide go? Oh, you have to hit that. Previous. There. So this is liters times, hold on, let me erase that, make that look pretty. Liters times kilopascals per Kelvin mole. Okay, and then let's see, over T, which is Kelvin times T. Yeah, there we go. All right, and then you are sitting over here multiplying by grams per mole. Grams per mole. All right, you algebra freaks out there. Look at all your units. This can be fun, right? Okay, let's just take our time here, okay? Basically, what you have over on this side is moles and moles cross-cancel. Let's see if we can cancel out anything else over on the other side. So what happens over here is if I extrapolate this out a little bit more, you'll get something like this. First of all, let's look inside of the denominator and see if we can cross-cancel stuff on the denominators. Kelvin here, Kelvin there, cross-cancel. So that's fun. You've got kilopascals on the numerator, kilopascals on the numerator of the fraction on the denominator. Are you as confused as I am? Basically what happens is the kilopascals does definitely cancel out. Let's try to be organized about how we do this. I'm going to rewrite what happens. This will be grams over liters on the left. On the right, technically this gram is on the numerator. Then you've got liters times mole. Liters times mole. And then look, that mole is still on the denominator. Mole. Check that out. That cross cancels. Look at what you have. Grams over liters equals grams over liters. Does anybody know what mass and volume relationship I'm really talking about here? This mass and volume relationship is called density. Isn't that amazing? You just reduced everything to density. Alright, so if you look at the very end conclusion, basically the formula becomes this. Check this. Density is equal to pressure times molarity, and I'm going to use the fancy M now, over RT. So look back at the original thing that I was showing you up here. See this right here? P over RT and that molarity, grams per mole. That is what I just turned this into. We realize that this is equal to density. That really is what it is equal to. When you cross-cancel all of your units, you will be left with grams over liters when you multiply P over RT by molarity. So, fabulous. This is just yet another use of the ideal gas law. So now, when we get the density of an object, or of a gas, I mean, you need to realize that that is equal to the pressure times molarity over RT. This formula is a tricky little bugger to remember when you're doing your AP exam, because they may ask you, they may give you the density, they may give you the ideal gas law, the temperature, the pressure, and they say, hey, what is its molar mass? And you're like, what? Where did they get that from? Don't forget this formula. And then if they give you its molar mass, the pressure, the temperature, you only need these three things to solve for the gas's density. Isn't that amazing? So check out Calculating Gas Density Sample Exercise 10.7. That is on the bottom of page 407. This is a great reminder to each of us, at least it should be a reminder to each of us, that this formula, the density formula with the ideal gas law, is easy to forget. So check out example 10.7 on the page, bottom of page 407. That'll be on your guided notes. Fast forward here. Okay, so it says, bottom here, it says, show me how these units cancel in your guided notes to give you density. And I just showed you how to do that, okay? And guys, we are done. I am going to continue for 10.6 to 10.9 for your next lecture series. So your next one will be from 10.6 to 10.9. Enjoy, guys. Adios.